Hi. Cool. So my name is Yury Selivanov. I'm from Toronto, Canada, but this is my first PyCon Canada talk. I hope you like it. So we're going to talk about high-performance networking in Python and Async IO. Quickly about me. I'm co-founder of Magic Stack. Check out our website, magic.io. I'm an avid Python user since 2008. Actually, one of the first versions of Python that I used seriously was Python 3.0 Alpha 4. And I've been using Python 3 ever since. So if you are still on Python 2, please give Python 3 a try. You'll definitely like it. I'm C Python core developer for almost 4 years now. In Python 3.3, I added inspect signature API. In Python 3.5, I added async await syntax. In Python 3.6, we'll be adding asynchronous generators and comprehensions. I maintain Async IO library with Guido, and I created uvloop. So the structure of this talk will quickly overview async await coroutines and what's coming in Python 3.6. We'll talk about async IO and uvloop. Then we'll talk about how you do I/O, how you implement protocols in async IO. This is the part of talk that is aimed for library developers and framework developers. Then we'll talk about Async PG, that's a high-performance Postgres driver, and then we'll recap. So async await. So in Python, there are 5 obvious ways how you do asynchronous I/O. You can do callbacks and deferreds. That's how Twisted started 15, maybe 20 years ago. You can do stackless Python or use greenlets. And probably all of you have heard about G-event. That's a library that uses it. Essentially, the syntax, the code looks like synchronous Python, but in reality, it is asynchronous. It's a little bit confusing, and that's the primary reason why stackless will never be mainstream. Since Python 2.5, it was possible to have coroutines using generators and yield expressions. In Python 3.3, we added yield from, and in Python 3.4, Async IO was born. And it used yield from syntax extensively. And in Python 3.5, we added async await, which is a native syntax. So why do I think that async await is a big deal? Well, first of all, it's a dedicated syntax. If you just open some source code and you look in it and you will see async await, you'll pretty much instantly understand. Okay, this is some network code. Before that, if you looked at coroutines, you would just see yields and yields from, and you had all kinds of questions like, is it a generator or is it a coroutine, and what is yield from actually? How yield from is different from yield? So the new syntax kind of answers all those questions. We also have pretty unique new concepts such as async for and async with. I don't know any language out there right now that supports this kind of stuff, and I don't even know how to code now without async with and asynchronous context managers. They are super useful. Another point about async await. It's generic, it's framework agnostic. If you don't like Async IO, you can build your own framework. That's what David Beasley did. He created Curio, which kind of works quite differently from Async IO internally. Async await is fast. It's only 2 times slower than a regular function call, which is fine, because in any program, asynchronous calls are completely dominated by synchronous calls. It's like hundreds of times more synchronous calls. So you won't even notice this small slowdown for async await, as opposed to coroutines that were implemented with yield expression, because those are like 100 times slower. Internally, async await and coroutines are subtypes of generators, but only in the implementation. So they share the same memory layout, they share all the code around them with generators, but on the Python level, they are completely distinct types. Await expression, for instance, it compiles to yield from internal. It uses the same opcode. We also have types coroutine, which was originally added to have backwards compatibility with old async IO code. What it essentially does, it allows you to await on a generator. And some people use it quite in quite an interesting way, like David Beasley. Basically, his library Curio is built all around this small decorator. We also have a bunch of magic methods. You can make an object awaitable, you can implement asynchronous iteration or asynchronous context managers using those magic methods. So in Python 3.6, we implemented async future and task in C, which will make your async IO programs up to 30% faster. And even if you use uvloop, it's still you're still going to see some benefit of it, up to 10% faster. We're also changing how async IO get event loop works. So I think we kind of did poor job of documenting async IO and documenting good practices, how to write async IO code. So a lot of them kind of just emerged on their own. And one of those was to pass event loop explicitly in your programs. So on one hand, you have nice async await, you have nice libraries designed around async await, but on the other hand, people just pass event loop everywhere. And this was because of the design flow in get event loop, and we are finally fixing it in Python 3.6. So the idea is that you just use async await, you never care about the event loop. Async IO will also have a pluggable async IO future. What this means is that frameworks like Twisted and Tornado, they can provide their own future implementations. So this is essentially a thing for interops. So you expect that pretty soon you will be able to just execute any Twisted or Tornado library in your async IO code, and this is a big deal. We'll also have async generators and comprehension. This small example shows a generator that just produces some sequence, and after producing each number, it sleeps for 1 second. And then we have an asynchronous list comprehension that builds a list out of it. This is a toy example, but it's pretty interesting what people can come up with using asynchronous generators. You can do all kinds of data processing pipelines with it. Let's talk about async IO, Cython, uvloop, and libuv. So async IO was created and right now developed and actively maintained by Guido van Rossum himself. Async IO is basically a toolbox. It's a low-level foundation for users to build frameworks on top. Nobody uses async IO directly. You have to use some kind of library. For instance, if you want to do HTTP, you will have to use AIO HTTP because HTTP is not part of async IO and probably never will be. Async IO is part of standard library, which is both good and bad. It's good because async IO is promised to be supported pretty much forever. It will be supported, maintained, we will add new features, so it's stable. You can trust async IO. It's bad because it's tied to Python release cycle, which is kind of slow. Async IO in Python 3.4 and 3.5 was provisional, which allowed us to push new functionality to bug fix releases, to point releases of Python 3.5. In Python 3.6, it's going to lose its provisional status, so you will only see new functionality in async IO in Python 3.7 now. What's inside async IO? Well, first of all, it has standardized pluggable event loops. So event loop is defined as a strict API, and you can actually swap the event loop implementation. That's what makes things like uvloop possible. It also has APIs and guidelines how you design protocols and transports and helpers to create servers and connections automatically for them. It has features and tasks which are essentially a bridge between async await world and callbacks world. We have asynchronous sub-process communication, we have queues, and if you like deadlocks, we have synchronous primitives like logs, events, and semaphores. So what is uvloop? Uvloop is a 99% compatible async IO event loop implementation. The idea is that you can just install it with basically one line of code, and your code becomes magically faster. It's written in Cython, and Cython is an amazing tool, actually. It's a superset of Python language. You can compile any Python program with Cython, and it will be 30% faster. But the real magic happens when you add static types information. Then you can actually achieve C-level performance with what looks like basically Python with some static types. uvloop uses libuv library under the hood. libuv is what drives Node.js. That's a cross-platform asynchronous I/O library developed for Node, used by Node. It's rock solid and it's fast. A lot of people invested a lot of resources to make libuv stable and good. So naturally, uvloop has super fast I/O because it uses only libuv. We don't even use Python standard socket module. Everything is done in libuv. So how fast is uvloop? On a small micro benchmark, like an Echo server, it's 2 to 4 times faster than Async IO. But I've heard a lot of good stories about using uvloop that makes real-world Async IO code 2 times faster. We also compared uvloop to different languages and different Python frameworks. And with uvloop, if you optimize your program correctly, you can actually achieve Golang level of network performance. So just use uvloop, and that was the slide I actually wanted to end my talk with. But unfortunately, it's not that easy. Just using uvloop won't make your code super fast. You have to use correct libraries to do that. So let's talk about how you can write fast libraries for Async IO. So this is basically one obvious way to do it episode 2. We have 3 different ways how you can code a protocol in Async IO. First, you can use low-level sock send all, receive, connect, accept methods, which essentially mirror blocking socket operations in Async IO. They just use async await. We can use high-level streaming API that allows you to just use async await and develop any kind of protocol on top. Or you can use low-level protocols and transports. So this is how loop socket methods look. We have two coroutines here. One just accepts sockets, and another just implements the Echo server functionality. As you can see, it looks similar to familiar blocking socket API. So this is naturally good. If you have a synchronous Python program that uses regular sockets, you can pretty easily convert it to coroutines using this approach. Streams, on the other hand, are much more higher level of abstraction. They are more performant than pure sockets just because the event loop, it knows more about your program. If you, let's say, read something from the socket, the event loop doesn't know, will you read more data, or will you just close the connection, or what will happen next? When you're using streams, the loop will continuously push the data to the stream. And then we have protocols and transports, which is basically callback hell. We have some basic guidelines how you write them. We have an API, but this is pretty complex. Downsides. So again, loop, event loop, and I/O multiplexers, they aren't aware of what really is going on when you're using low-level socket coroutines. So they are good for prototyping, they are good for porting code, but it's not possible to write efficient libraries with them. Streams are nice, a little bit more performance than using low-level socket methods, but they're too generic. You are basically forced to build the entire protocol in Python, which is slow. And protocols and transports, yes, they use callbacks, they're hard to use, but they allow you to implement the bulk of your protocol in C or in Python or in Rust, like whatever you actually want, and then bridge that code to Async IO. So use socket methods for prototyping or for porting existing code fast. Use streams again for prototyping or for implementing decent protocols that will run just okay. And if you want super fast, super good performance, just use protocols and transports. So let's focus on protocols. A loop always pushes data to protocols. You don't even read the data in protocols. What you have a hook method that just accepts the data, and data is continuously pushed to the protocol. Protocols can send data back using transports. And protocols can implement read and write buffers. Well, basically, you are on your own how you want to process the data. Protocols can do flow control. You can say you can tell the event loop, please stop sending me the data. You can adjust low watermarks, high watermarks. You can do a lot of hints how the I/O should be performed. Essentially, you have full control over the I/O when you use protocols. So if you want to implement a high-performance library, you basically have two choices. Strategy number one is to develop custom streaming abstraction using Python, using async await. And a good example of that is AIO HTTP. It's fine. Its code is pretty readable. It's pure Python, but it's not as fast as it could be. Strategy number two is to implement everything using callbacks and using C or Python. And then have a nice small layer of async await compatibility. That's how you do it. A good example of that is Async PG. So let's talk about Async PG. Async PG is the fastest Postgres driver for Python out there. And we also profiled a couple of other languages like Go and Node.js. Async PG is faster. It's written from scratch in Python and Python. And it doesn't use libpq. libpq is the library that ships with Postgres. And that's the library that almost everybody is using to implement Postgres in Python. For instance, scikit-pg2, it uses libpq. So Async PG, first of all, it uses binary data format. If you are implementing a protocol and you have two options, a text protocol and binary protocol, always go for binary because it's less data, which means less traffic, which means faster I/O. And usually you can parse binary protocols much faster and much more reliable, by the way, as well. And speaking of reliability, not all Postgres types can actually be unambiguously parsed when they are transmitted as text, but all of them can be if they are transmitted as binary. So always choose binary if you can. When we started to design Async PG library, we thought a lot about the API, like how it should look like. And one of the options was to just use Python DB API, just add some async await on top of it, and that's it. But we realized that Python DB API isn't really good because it's a common ground for all databases, and you cannot actually use Postgres efficiently using just DB API. So we decided, okay, let's build efficient API just to utilize Postgres efficiently. So one of the things that we do in Async PG, we use prepared statements. We use them extensively. Even when you aren't using it explicitly, we create implicit statements automatically for you. The idea is that the prepared statement can be parsed only once on the server side, and then Postgres can just reuse it. And we also dynamically build the pipeline for encoding and decoding data for prepared statements. So why am I telling you all of this? It's when you are designing a new library, you have to sometimes take a look at what you are doing it for, and you have to optimize this library for this thing. Just forget about all the things that exist right now, because maybe you can do it better. And that's what we did with Async PG. And it kind of shows, because Async PG is 2 times faster than anything that we've benchmarked. It's 10 times faster than libraries for Node.js. And it's 2 times faster than even libraries for Go that are written in pure Go. The architecture of Async PG is kind of simple, actually. We have 2 core classes. One is core protocol and another is protocol. Core protocol knows nothing about I/O. It just receives the data and it parses it. And protocol is the bridge. It's the bridge that connects this low-level protocol to async await. So how do you parse Postgres protocol? It's quite complex, actually. We have 2 approaches. Naive approach is just to do it in Python. Just use bytes, just use memory views. But the problem is that when you use Python objects, you will do a lot of memory allocations. There is a huge Python C API layer on top of your data, so it's going to be slow. The other way is to use Python and to use or C, and to use low-level C data types, and to write high-level buffers that just abstract those C data types with a nice API. So, for instance, in Async PG, we have 3 different kinds of buffers to optimize for different protocol use cases. And on top of all of that, we have nice async await facade. So this is how Async PG code looks in real life. As you can see, it's all about async await. It's all about usability. Even though underneath it all, we have callbacks and we have complex data processing pipelines and stuff like that. So let's recap. First of all, if you are a framework or a library author, don't be afraid of protocol. You are almost obligated to check them out. Take a look at them. It's the only way to write high-performance code in Python, high-performance libraries and frameworks, because that's the only way how you can do stuff in C. Use Cython. Cython is amazing. A lot of code out there is written using Cython. Basically, half of the Python scientific infrastructure is written using Cython. Its syntax is relatively easy to learn. It looks like Python, and your code will be faster. And it has a lot of instrumentation. Async await should always be the preferred API in your library. Never expose callbacks stuff just because nobody will use it, and it will just create extra level of confusion. Async await should be the way to go. And the idea is that once you have fast drivers and fast libraries, your async await code will be fast. Like if you have a fast memcache driver, if you have a fast database driver, then you can actually optimize for the fast pass in your application. And it's going to be fast. Always use binary protocols. Again, never choose text. Text is much slower to parse. Always profile your code. This is actually an interesting story because we created Async PG. We used all those advices basically. We used Cython extensively, and when we first profiled Async PG, it was 2 times slower than PG, and it didn't make any sense. So after a week of profiling, we made it 4 times faster in some cases. So always challenge yourself. Always profile, and it will improve the code. Cython can actually be profiled with ball grind. You can visualize results with kcache grind. It's a really convenient tool to work with. It also has a -a option, which essentially generates HTML files with your Cython code in them. And each line will be highlighted. It will be pure white if it's fine, and it will be yellow if it's slow. So it's really easy for you to optimize your Cython programs. Try to do zero copy. If you go down to the C data types in Cython, you can actually try to avoid memory allocations. For instance, if you are building a response object, what you can do, you can actually over-allocate your buffer, and then you to have just one memory allocation. You can write your stuff and then dump your data with a single transport.write. If you don't have control over how many writes your protocol is making, you can use TCP cork and TCP uncork options, which essentially tell the kernel that I will do a bunch of socket send operations right now. Don't send them right away. Wait until I uncork the connection and just send them in as less TCP packets as possible. Use TCP no delay. This advice actually applies to Python 3.5 mostly and Python 3.4, because in 3.6 we use TCP no delay automatically and by default. Also, consider implementing timeouts as part of your API, because you can implement them much more efficiently in the lower level of your protocol. Async IO has facilities to make timeouts easy. It has wait for, but it's kind of slow. That's it.
Thank you, Yury. That was a great talk. Does anybody have any questions? Talked about a lot of material, and I'm sure many minds are churning. Okay, I will go first then.
That was unexpected. Okay.
Why did you spend the time to do all of this and write all of these different libraries? Like, what is the underlying use case that led you to want to make the networking protocols faster?
Well, that's an interesting question, actually. So at Magic Stack, we're building a new database. It's called EdgeDB, and I really recommend you to check it out. It's not yet open source, But the idea is that it's an object-oriented database, and it's built on top of Postgres. And the layer that is written, the translation layer, is implemented in Python, basically. So we needed a way to implement this layer as efficiently as possible, because we are writing it in Python, because it would be impossible for us to implement it in C. It's just too much code. So that's one of the reasons, basically, that motivated us to first explore libuv and implement uvloop, then to actually fix bugs and add features to async IO in Python, because we needed them ourselves. It motivated us to create a proper Postgres driver, because Async PG uses text protocol, and it's a pain to work with some types, with some Postgres types. And it's also slow, so we needed as fast option as possible. So yeah, we kind of just scratched our own itches.
All right, who's next?
This is a bit of a follow-up for you. You mentioned you're building EdgeDB, which you said is an object-oriented database built on top of Postgres.
Yes.
What's the motivator for EdgeDB? Sorry.
Basically, to develop software faster. If you look at any application basically out there that uses a relational database, you pretty much need to use ORMs. And ORMs are convenient, but that's one extra step that you have to do. There is no asynchronous ORMs for Python, and I don't think it's even possible to port, let's say, SQL Alchemy to Python, just because it's architectured in that way. So what we did in EdgeDB, we looked at the data structures, at the actual relational model, and we thought how we can make it better. And I think we took a lot of inspiration from Python, because in EdgeDB we have multiple inheritance. We efficiently compile this data representation to the relational database. We have all this. We have strict schema. We can introspect that schema. We can generate automatically React.js bindings on top of it. So it's a lot of magic that we can do in EdgeDB. And if you look at a regular, like at any modern application out there, you will see that roughly 50% of the code just pulls data from the database, applies some basic transformation to it, and then pushes it back to the client. And one part of that transformation is security, the ACL, the access layer control. And everybody just hard codes it. In EdgeDB, we have policies. We just tell how it should work. You clearly separate visibility layers as part of the schema declaration, and we can do that completely automatically. So the idea with EdgeDB is that it allows you to develop your applications much faster. It's essentially as fast as you would use MongoDB, but in MongoDB you don't have any schema. So eventually, at some point of time when your application grows, you will start to re-implement this strict schema in your application. In EdgeDB, you can develop it super fast, and it has schema, and it has stuff like React.js integration, like out of the box, and GraphQL, by the way, as well. We support GraphQL spec fully.
Thanks for your talk, Yury. I don't interact with networking code a lot, but I came to your talk because I wanted to see some examples of what are some problems and some places where people need to optimize these kinds of communications. Typically, I think of networking, I think of actually web applications. And so it was a really great example to see this connection between your application code and the database just at that level, and to see where there are chances to optimize. I'm wondering if you have some other examples from this world that show the use of these techniques.
I don't have them in the slides, but I can tell you that probably one of the best examples out there right now is WebSockets. So it's not possible to implement WebSockets in Django, let's say, or Flask. You have to use something else. You have to handle those concurrent connections, and a lot of them, actually. And the problem with WebSockets specifically is that a lot of those connections to the server, they do nothing. They just sit there, and once you need to call some function, or once you need to send some data, you use it. But otherwise, it's kind of just sitting there. And it's not possible to use Python Python processes or threads to handle that, because if you have tens of hundreds of thousands of users, you just will run out of resources. So that's where you use Async IO, because it will allow you to efficiently just have those hundreds of WebSockets, or thousands of them, open and just waiting for the stuff. Yeah.
Quick round of applause for Yury.
Thank you.